Hello and welcome to Earth Science. So this unit is going to be the absolute ages of rocks. Our previous unit was the relative age, so we're going to go and kind of tell you the difference between both of those. So relative versus absolute age. Well, absolute age, as you can imagine, is your absolute age. It's your age in numbers or an object's age in numbers. So the example here I have is you are blank years old. So I am 25 years old. That's my absolute age. Now, my relative age would be like a comparison. So compared to my other siblings, I am the youngest sibling. My absolute age is 25 years old, but my relative age is the youngest. So I hope that makes sense for you. It's a pretty simple concept, but if you're not getting it, go ahead and let me know because I want to be able to make sure that you can understand the differences between both of these if my examples aren't quite working out for you. So really just remember absolute age, we use this thing called radiometric dating so that we can find the exact number of isotopes in, or the exact number of isotopes in a certain object, so like a rock, that's how we get absolute age. It is an exact number of things inside of something. Whereas the relative age, which we've gone over before, is kind of like with the law of superposition, how younger rocks are on top and older rocks are on bottom. So the top rock is younger relative to the bottom rock. It has nothing to do with absolute age. It just has to do with the comparison of age between the top rock and the bottom rock. That's its relative age. Its absolute age would be found probably in the millions of years. So the top rock would be like 65 million years old, and that's its absolute age. And the bottom rock would be around 300 million years old, and that would be its absolute age. The thing about rocks is that we use relative age because absolute or radiometric dating tends to only go back about 75,000 years, and I'll tell you why. So we use this thing called radiometric dating for finding the absolute age of something that's really old. And essentially, we're just using the properties of radioactive decay. So it sounds like a really big, complex thing, but all it means is everything is radioactive. So you, the table that you're sitting or that you're putting your computer on, the chair that you're sitting in, all of that is radioactive. Things are flying off of it all the time. Things are coming into it. It's just really things, elements in your body are moving off of you. They're decaying off of you, but other elements are coming in and combining with certain elements on you as well. So the idea of radioactive decay is that certain elements, which are the building blocks of all materials, have isotopes. And so an isotope is just an element with a different number of neutrons than is normally found in nature. So normally carbon is C12, but the isotope is C14. So that means that it's got 14 neutrons. It still has 12 protons, but the neutrons are what changes. So that's the interesting thing about isotopes that you're going to want to know is that an isotope is an element with a different number of neutrons. So it's still got, the same properties of that element, which is what the electrons and the protons decide, but it's got different neutrons, so it acts a little differently. And so they're relatively rare, but they're found pretty commonly throughout many materials, especially rocks. So we use these relatively rare isotopes because we can find them a lot easier in rocks, and then we look at how much it's decayed and we can quantify the amount of time that it takes for certain isotopes to decay. And so then that makes it so that we are able to kind of go backwards with how many isotopes we have found in the element versus how many we normally find. So, a good example right here would be the half-life of carbon-14 is 5,730 years. So imagine we find a rock that has about 1/4 the amount of carbon-14 isotopes that we would normally find with that element being in a concentration inside of a rock. So with 1/4 of those isotopes in that rock, we're going to safely assume that four half-lives have gone through, or two half-lives, excuse me, two half-lives have gone through. So one half-life makes one half, another half-life makes one quarter. So we'll say that two half-lives have gone through since there's only one quarter of the amount of carbon-14 that we would normally find in this isotope or in this rock. And so then we would just multiply this by two. So we would find that the half-life of that particular isotope is actually, looks like it'd be 1160 years. And so that's how old that rock would be. So I'll get into it a little more as well. Isotopes decay over time. That's that decay I was telling you about, how our bodies just kind of give off elements. They just decay into other elements, basically, is what's happening. And then the half-life, you know, it's pretty self-explanatory. It's the number of years it takes for an element to break down one half of itself. So that's why we call it the half-life. And so we know how long this decay takes. I told you already about the carbon-14. How we figure out how much of the carbon-14 is in an element or in a rock is we find the amount of nitrogen-14 inside of that. And the reason we do that is because carbon-14 decays. Remember, this radioactive decay kind of goes away. It decays into nitrogen-14. So if you have 25% carbon-14 in a rock and 75% nitrogen-14, that means that we've gotten to one quarter of the carbon-14, so that's been two half-lives. And so that goes back to that example I was talking about a minute ago, where we can then take those two half-lives, multiply this by two, and we find out how old that rock actually is. So here's an example so that you can kind of see what I'm talking about here. So they pick an element in a rock, and then they determine the half-life and the amount left of that element in the rock. So for this example, we've got uranium. So let's go up here and find uranium right here. Uranium-235, that's the isotope. Remember, an isotope is just an element with an uncommon number of neutrons. So in an element, we've got electrons, protons, and neutrons. The electrons and protons stay the same. The neutrons are what change. So we've got uranium-235 here, that's the isotope, and that decays into lead-207, and lead's little misnomer here, not misnomer, but the letters that we associate lead with is Pb, because the Latin word for lead is plumbum. So fun fact there. So anyway, the uranium-235 decays into lead-207, and that takes about 704 million years. So for the sake of this little figure right here, we're going to say that it takes 1 billion years. We're rounding up from 704. So here we go. We've got a rock. We've found the element that we want to survey, we want to look at with a microscope. So we found uranium. Okay, so we're going to look at this uranium, say right here. We look at the uranium in this rock and we notice that there's about, I don't know, 1/8% of, or that would be about 12.5% of uranium compared to lead. So the rest of it is lead. 12.5% of the elements in this rock that are uranium, or excuse me, 12.5% of the elements in this rock are uranium. The other 77.5% of the elements are plumbum, which is lead. So that means that it's taken 3 half-lives, because we're now at 1/8. So we start at 100%, we go to 1/2, we go to 1/4, and then we go to 1/8, which is 3 half-lives. So we've noticed that there's 1/8 the amount of uranium that we would normally find in this rock, whereas there are 7/8 of this decayed lead, which used to be uranium. So then we're able to say, okay, that's been 3 half-lives. Okay, let's go to the chart. How long does it take for uranium to go through one half-life? 704 million years. For the sake of this figure, 1 billion years. So it's been 3 half-lives, so that's 3 billion years. That's really the essential nuts and bolts of the absolute dating of rocks. I gave you probably a little more than you're going to need to know for the quiz, the tests, and the midterms. But, you know, the more you know, the better you are. that type of thing. So if you have any questions, comments, or concerns, go ahead and let me know. Otherwise, have a wonderful week, and we'll see you on the next one.